Today we are going to be learning partial fraction decomposition. So let's take a look about what this is. We know how to add rational functions. We get a common denominator, take care of the numerator, get a common denominator, and then reduce the numerator, right? So we know that this is equal to this. They are equal. But what if we started with this? What if we started with it this way and wanted to know what the two rational functions were that add to make this? We want to decompose this rational function into its partial fractions. That's what partial fraction decomposition is. Why in the world would we want to do this? Well, because in calculus, when we're finding antiderivatives or integrals of rational functions, we must decompose some of these rational functions. If the denominator can be factored, we need to do this process. We need to decompose this function into its partial fractions so that we can integrate. This cannot be integrated as it is. This is extraordinarily easy to integrate. It's a one-step. Once I get to here, it's a one-step integration. I just write the answer. This antiderivative is 2 ln absolute value x minus 3 minus ln absolute value x plus 2. Very easy to integrate. Okay? FYI. Alrighty. I hope you like my little people here. Alright. Partial fraction decomposition then. So there are three kind of situations that you're going to come across. And the first one is when you get distinct linear pairs. So in this denominator can be factored into x minus 3, x plus 2. Those are distinct, meaning they're not repeated, and they are linear, meaning each one would be the equation. It has a degree 1. Each has a degree 1, and they are distinct. All right, distinct linear pair. Okay, so that's the first situation, and we already know this is the same one that we had up here, so we already know what the answer is going to be, but let's see how we would get there. All right, so I'm going to write this out. I'm going to write this with its factored form in the denominator because this gives us what our two denominators are going to be. It's what would be added to get this. It's what we would have before we got the common denominator. This is the common denominator. So what could the two denominators be? Well, there's only two things, right? This type is the easiest of the three types that we're going to learn because there's only one thing it could be. All right. Now we do not know what the numerator is. We just do not know. So but we do know that it's going to be a number. Right? There won't be x's up here. It's just a number because these are linear. Because these are linear, you will not have x's up here, just numbers. I'm going to call those numbers a and b, and we'll find out what is a and what is b. So now I have this equation, and to solve this equation, I'm going to multiply both sides by the common denominator. Since it's an equation now, I can do that. I'm going to multiply both sides by the common denominator, x plus 2, x minus 3. I have no idea why I wrote the x plus 2 first. Usually I would write whatever order it came in here, but whichever means the same thing. Multiplication is commutative most of the time. Alrighty, so here these denominators reduce out, and we just are left with x plus 7. Over here, the x minus 3, when we multiply this, the x minus 3's cancel. I'm left with a times x plus 2 plus b times x minus 3. And now we're looking for the values of a and b that make this thing true. For all values of x, we want this to be true. Okay? So we're going to randomly choose any value of x that we want to find a and b. All right? So what would be convenient values to choose? We can pick anything we want. What would be convenient? Well, if I want to find out what A is, it would sure be nice if B was not involved. True? So if I let X be 3, then I will not need to worry about B at all, and I'll be able to find A immediately. So I'm going to begin by letting X equals 3. If X is 3, then this side would be 10, and I would have A times 5 plus 0, right? B times 0 is just 0. This tells me that A has got to be 2. So now we know what A is. All right? See if I can get another color here. Maybe I'll do red. Okay. Let's let X be another convenient value for this situation. Well, another convenient value here would be a -2. So I'm going to let X be -2. If X is -2, this will be 5 on this side. This will be 0. And this will be B times a -5. Right? So that tells me that B has got to be a -1. So I can go back now and say that this fraction that we started with, so therefore x plus 7 over x squared minus x minus 6 is equal to 2 over x minus 3 plus -1 over x plus 2. And that is what we got up here. 2 over x minus 3 plus -1 over x plus 2. Okay? So that is the partial fraction decomposition of that rational function. All right. So that's the first type, where you have distinct linear pairs. Let's do another type. Let's do where we have repeated linear factors. I bet you that said factors instead of pairs. I don't know why I said pairs. I need to go fix that. I think that should be factors. Okay. Repeated linear factors. So in this one, how would that factor? Well, that would factor into, I think I'm going to do it up here just to save some room. So I'm going to take out an x to begin with. And then that factors into x times x plus 1 times x plus 1. It's being squared, right? X plus 1 squared. It's repeated. X plus 1 is repeated. So repeated linear factors. Individually, they're both linear, but this one is being repeated. Okay? So when I write this out, I'm going to say 3x plus 6 divided by x times x plus 1 squared is equal to. All right. So, in class I would ask, tell me, what could the individual fractions be that would add to this? Well, definitely we could have something over x. True? So I'm going to make it a over x. Definitely something over x. What about this one? What could that be? Well, it could be something over what I'm looking at, the x plus 1 squared. Or there is a possibility that we could have another fraction, and its denominator would just be a single one of these. If I were adding these together, what would the common denominator be? The common denominator would be this. So I have to consider all three of these situations. Okay? That's what you do when a factor is being repeated in that bottom. Now, each one is linear. So each numerator has to just be a number, no x's. All right? Okay, so I'm going to do the same thing that we did before. I'm going to multiply both sides by the common denominator. The common denominator is x times x plus 1 squared. and then I would get 3x squared plus 6 is equal to a times, the x's cancel, I'm left with x plus 1 squared, plus b times, the x plus 1 squareds cancel, I'm left with b times x there, plus c times, okay, one of the x plus 1s is going to cancel, I'm left with x times the other x plus 1. All right. Time to let things happen here. So, first of all, let's see. First of all, what is a convenient x to, what is a convenient value to let x be? Well, if I let x be -1, it would get rid of this, it would get rid of this, and I'd be left with b. So let me do that. I'm going to let x be -1. If x is -1, on this side I'm going to have just 3 plus 6 is 9. This is gone. This will be a b times -1, and this is gone. That gives me the value of b. b has got to be -9. Okay? Next. How about 0? What if we let x be 0? If we let x be 0, I wouldn't have that piece, and I wouldn't have this piece. I would only have a. That'll work out good. So this is just going to give me 6 on the left. This is going to be a times 1. Everything else is 0. b has got to be 6. I'm sorry, a has got to be 6. I was looking above. A has got to be 6. So far we have a and we have b. Now to get c. All right, what else can we let x equal here? What else can we let x equal? Well, what other convenient value is there? Well, nothing is going to get rid of what we, do the same thing. So we can let x be any other number you want. Any other number. We tried -1, we tried 0. What's another easy number to put in for x? How about 1? If we put 1 in for x, I'm going to have the 3 plus 6 again, so I'll have 9 on the left. I'm going to have a times 1 plus 1 squared. But we already know a. So we already know that a is 6. So we'll have 6 times 1 plus 1 is 2, squared is 4. Plus b times, well, I already know what b is. b is -9 times x, which is 1, plus c, we don't know c, times 1 times 1 plus 1. So this is going to allow us to find the value of c. So therefore, this is 24 minus 9, that's 15. 9, so our equation is going to be 9 is equal to 15 plus 2c. If you subtract 15 from both sides, get -6 is 2c, which tells me that c has got to be -3. So now we know a, b, and c, and we can say we're in an FRQ, you want to, state your answers. So I'm going to say, therefore, our original function decomposes into 6 over x plus -9 over x plus 1 squared plus -3 over x plus 1. Yeah. Now yes, we could have made this 6 over x minus 9 over this, minus 3 over that. So yeah, you can also write it like that. I like to leave it with plus because I know where we're going with it. And in calculus, you can do it either way, to be honest with you, but I like to leave it in plus. It reminds students to make it a -9 there. So, okay, so that is repeated linear factors. That's the second type. And now for the third type, distinct linear and quadratic factors. Quadratic. Okay, so let's see what that does. Let's factor this denominator. How does the denominator factor? Well, I can take out an x, and I'm left with x squared plus 4. How do we factor that? It doesn't. This is a quadratic factor because it's quadratic, yeah? All right. So we have a linear and we have a quadratic. Neither is repeated though. The factor is not being squared. Okay? Neither is repeated. They are distinct. If they were repeated, we'd have to combine what we're doing here with what we did up above. Okay? Alrighty, so I can write this as 3x squared plus 4x plus 4 divided by x times x squared plus 4 is equal to. Alright, well the first factor here is x, so that's an easy one, a over x. The second one, it's not being repeated, so I'm just going to have a single. I'm not going to have a third fraction here, okay? However, what can be up on top? A is just a number because I have a linear, a power of an x to the first on the bottom, so there cannot be x's on top. But here I have x squared, so I might have an x on top. I also might have a constant with that on top. So I could have a linear equation up here, bx plus c. Okay? So we're going to find the value of a, b, and c. Just like we've been doing, I'm going to multiply both sides by the common denominator. On the left, I'll have the 3x squared plus 4x plus 4. And this on the right, I'll have a times the x squared plus 4 plus, okay, the x squared plus 4 is canceled, and I have the x here, right? So bx times x would be bx squared plus cx, right? Okay. Time to let x be something. Well, a convenient value to let x be would be 0. If I let x be 0, I would get the value of a. So I'm going to let x be 0. And if x is 0, on the left I just have 4. On the right I have a times 4. That tells me that a is 1. So now I know a is 1. All right. What other value of x would be convenient here? Nothing is going to get rid of this. So I would just pick 1. Let's pick x is equal to 1. Let me go with another color. Alright, if x is 1, I'm going to have 3 plus 4 plus 4, that's 11. If x is 1, I'm going to have 5 here. I know that a is 1, so 1 times 5 is 5. Okay? Plus b plus c, if x is 1, right? That is 2 unknowns and 1 equation. We can't do anything with this. I can move the 5 over. I know that b plus c must be 6. But b and c, right now, b and c could be tons of things. We need to go get another equation, right? So let's get the equation. I don't know why I'm having a hard time coming up with different colors here. Let's get the equation, let's get the value of x. X is equal to -1. That's another nice value. So if x is -1, I have positive 3 minus 4 plus 4, which is just positive 3. Okay? A is still 1. And then I'll have -1 squared is 1, 5. So this is still 5. Plus bx squared, so -1 squared is 1, so that's plus b, but I'll have a minus c. And that tells me that b minus c has to equal -2, right? Okay, Now this is good because I have two equations and two unknowns, so I can find the values of these unknowns. I'm going to add the two equations together. You see I lined them up nicely. I'm adding the two together because that'll get rid of the c's. B plus b is 2b. C plus negative c is 0. 6 plus negative 2 is 4. This tells me that b must be 2. I know that b plus c is 6. So 2 plus c is 6, so c must be 4. So I have the value of a, b, and c, and I can state my answer as 3x squared plus 4x plus 4 over the x cubed plus 4x is equal to 1 over x plus 6x plus 4 over x squared plus 4. And those are the three types of what we're going to be, of partial fraction decomposition. And of course, the denominators can get quite complicated. These can get quite long. We could have repeated quadratic factors where we would have two of these things. They can get quite complicated, all right? I will tell you though, for AP Calculus, the only kind you'll have are the distinct linear factors. Distinct linear factors, okay? They'd only be like this. They tend to be quite short, all right, for calculus. Also, on the AP Precalculus test, the only thing that they test are distinct linear factors, okay? So this is the only type on the AP exam, both AP Precal and AP Calculus, all right? The other ones are great to know. When I took calculus in college, we did calculus problems like this where we would start with this integral and we'd have to get the partial fraction decomposition and then integrate. Once you get the partial fraction decomposition, these are all very easy to integrate, all right? So it's not a problem once you get there. You just have to get there first. Okay, for the rest of the time I have some random examples. So here I'm not telling you which type it is though. So we'll have to figure it out as we go. All right, factor this. This factors into x plus 5, x minus 2, distinct linear factors. This is the kind that's on the AP exams. All right, so I'm going to have the numerator over x plus 5, x minus 2 is equal to a over x plus 5 plus b over x minus 2. Easy peasy. I'm going to multiply both sides by the common denominator, but I'm not going to show that I'm doing that, okay? But that's what I'm doing. To get to my next line, I'm multiplying both sides by the common denominator. I'm going to be left with the numerator over here. The a is going to be multiplied by the x minus 2. The b is going to be multiplied by the x plus 5. Easy peasy. Don't overcomplicate this. Easy peasy, all right? Okay, what should we let x be? Let's let x be 2. If we let x be 2, I'll have a 2 on the left. A zeroes out, and here we have 7b, which means that b is 2 over 7. Let's let x be negative 5. If I let x be negative 5, 4 minus negative 5 is 9. I'll have negative 7a, and then this is zeroes out. And so we get that a is a negative 9 over 7. So I know that my partial fraction decomposition, my answer, this rational function is the same as negative 9 over 7, that was a, right, over, make sure you get it over the correct denominator, plus 2 over 7 all over x minus 2. And it is perfectly fine to leave it in this form, okay? Perfectly fine. If you just couldn't stand it and wanted to do something with it, I would multiply here, I would multiply top and bottom by 7, and I would have negative 9 over 7 times x plus 5, plus here I would also multiply top and bottom by 7 over 7, 2 over 7 times x minus 2. And there's nothing wrong with writing it like that either, but you are welcome to stop right there. Okay? I believe. I'll check on the AP exam stuff, but anyway, yes. Okay, what about this one? Partial fraction decomposition. We begin by factoring this bottom. Let's factor this bottom. How does the difference of cubes factor? Well, difference of cubes factors into x minus 1 times the square of the first, change the sign, multiply them together, the square of the last. That's how you factor a sum or a difference of cubes. For the signs, you begin with the same sign, then it's the opposite sign, and then it's always positive at the end. Always positive at the end. Okay? Alrighty. So, does this factor further? No. If this was already, if you could not take out a GCF, if you cannot take out a GCF, this will never be able to be factored if it was a difference or a sum of cubes. Okay? No GCF, so you can't factor that. Alrighty. So, we have a quadratic over here. True? Linear? Quadratic. So when I write, x over x minus 1 times x squared plus x plus 1, I'm going to have two factors, a over x minus 1 plus, okay, since my denominator is quadratic, I could have a linear numerator, bx plus c. Alrighty? That's how we do it. Okie doke. So, by the way, keep in mind that when we're finding a, b, and c, a is not going to be 0, for sure, but b or c could be 0. B or c could be 0 here, okay? Alrighty, multiply both sides by the common denominator. On the left, I'm just going to have the x, because the common denominator is that. On the right, a is going to be multiplied by the x squared plus x plus 1, and this bx plus c is going to be multiplied by this. True? So either way, you can split up the bx and the c, or you can just leave it like this. Either way is fine, okay? You could have said bx times x minus 1 plus c times x minus 1. If you prefer that, go ahead and do it. Either way. Okay, time to let x be some things. So let's let x be a 1. Let's let x be a 1. So if we have x is 1, then I'll have a 1 on this side. I'll have 1 plus 1 plus 1, a times 3. 0 times that is gone. So a is going to be 1/3. Now I know what a is, 1/3. Perfect. Now for the other one. So this, I said, cannot be factored further. This, this is not going to have any zeros in it either. Okay? If I use the quadratic formula on this, I would see that I got imaginary answers. So this doesn't cross the x-axis at all. Okay? So I can't let x be something that's going to get rid of that. So instead, I just let x be anything else. Let's try 0. If we let x be 0, I have 0 on this side. I have 1 times a, but a is 1/3, so 1 times 1/3 is 1/3, plus b times 0 is 0, plus c times -1. Yeah? So 0 is 1/3 plus c times -1. C has got to be 1/3, right? the only way we could get 0 over here. True? All right, now we know that c is also 1/3. Let's let x be a negative 1. We'll have a negative 1 is equal to, all right, 1 minus 1 plus 1. It's still just a, so 3. 1/3, I mean. Plus b times a negative 1 is negative b, plus c, and I know c is a third, times negative 1 minus 1 is a negative 2. I'm going to come over here and do a little work here. So let's see. I have negative 1 is 1/3 plus 2b minus 2/3, right? So negative 1 is equal to negative 1/3 plus 2b. Add a third to this side, and I'm going to get negative 2/3 is 2b. Divide both sides by 2. If I divide both sides by 2, the 2's will cancel, and I get b is a negative 1/3. So b is negative 1/3. And so my answer here, x over x cubed minus 1 is 1/3 over x minus 1 plus 1/3 x, negative 1/3 x plus 1/3 divided by x squared plus x plus 1. Okay, and again, another way to write that would be move this 3 to the bottom. So 1 over 3 times x minus 1 plus, if I multiply top and bottom by 3, it's going to get rid of this 3 and that 3. So I'll have negative x plus 1 on top, 3 times that on the bottom. Okay, very good. Very good. One more. Let's see what time we're at. 32 minutes. Okie dokie. One more that I had here for us to do. Okay. How does this denominator factor? Well, this denominator factors into x plus 1 times x plus 1. Okay, so we have a repeated linear factor. We're not going to need the ax plus b because this is linear, but we are going to need to deal with that. So I have 2x minus 3 divided by x plus 1 squared. So a over x plus 1 squared plus b over the single factor. Those are my possibilities, right? Those are the possibilities. I'm going to need to pause this real quick. I am taking care of my daughter's bunny, and I keep hearing him chewing on something, so I was checking it out. Okay, alrighty, back to this last problem. Okey-doke. Here we have it. So we're going to multiply both sides by the common denominator, and we're going to get just the numerator over on this side. Just a right there, right? If I multiply both sides by x plus 1 squared, just a plus b times another x plus 1. Okay? That's how that would go. So let's let x be a convenient value. So if we let x be negative 1, if we let x be negative 1, I'm going to have negative 2 minus 3 is negative 5. I'll have a, and then this will be 0. So immediately we get a. A is negative 5. Yay. That was good. How about if we let x be something else, anything else? Let's let x be 0. I like to let x be 0 when I can. So 0 minus 3 is negative 3. We'll have a plus b, which is, a is negative 5, plus b times 1. So this tells me that b is 2. Wow, that turned out to be nice and easy. So we have 2x minus 3 divided by x squared plus 2x plus 1 is negative 5 over x plus 1 squared plus 2 over x plus 1. And keep in mind, you can always check these. You can always check these. Start with this. Get a common denominator. If I were getting a common denominator, the common denominator would be x plus 1 squared. We'd have the negative 5 that wouldn't have to be multiplied by anything, and we'd have 2 times x plus 1. Yeah? This is negative 5 plus 2x plus 2 over x plus 1 squared, which is 2x minus 3 over x plus 1 squared. And that is precisely what we started with. You can always check your answer. Either algebraically you can check it, or you can also check it graphically. If I were to put in, and I am to put in, I'm going to put in what I started with, the numerator in parentheses, divided by the denominator in parentheses. There's my first function, and I'm going to put in the second one. So negative 5 divided by x plus 1 squared. Can you hear the bunny over there going through some papers? Okay, plus 2 divided by parentheses x plus 1. When I graph this, I'm going to first see the first function. That'll be in blue, and then I'll see the second function. That'll be in red. They should line up. If they don't line up, I've done something wrong. And they do line up, of course. Okay? So you can check it graphically or algebraically. Every one of these. You never have to wonder, I wonder if I did something wrong. If you did something wrong, you'll see it when you try to check it. Okay, and that is partial fraction decomposition. The only type that's on the AP exam is the distinct linear pairs. Okay? Alrighty.